So while I was eating that cupcake, Tyler made a point in the chat that I just happened to see. There's probably been lots of good comments in the chat, but I can't read them all right now. But I happened to see Tyler's comment, which I thought was great. He said, hey, it's hard to call it metaprogramming when all you're doing is regular programming at compile time. But that's the point. Metaprogramming, as you would stereotypically think of it, is hard to think about. It's hard to reason about because you've got this meta thing that's separate from your regular thing, and who knows what's going on, right? And the point here is that we're bringing the meta as close to what you regularly do as possible. So it's just normal stuff that you're used to thinking about, that you're used to being very effective in, right? And let's bring that effectivity over to what is normally considered the meta part. So that's what we're doing. We're trying to make metaprogramming as boring and normal as regular programming because the exciting part should be what you're doing, right? It should be the task you're accomplishing, not, language complications, right? We want the language to be as simple as possible, but no simpler, to use that old chestnut. Okay. Now, probably some other people were saying this in the comments. This starts to get hard to read because we've got this sum function, but then we've dropped this giant modify function in there. And you know what? It's dwarfing the original function. And depending on what we want to do in here, it could get more and more complex. Also, maybe we want to share this modify code. If we're doing an operation commonly, we want to share that among many things. So as it happens, this doesn't have to be specified right here, right? You could refer to it by name somewhere else. And so down here, we've pasted exactly the same thing. So here's our sum function, but we've given a modify proc by name, ensure R is big enough. And we've done ensure R is big enough here, and we've taken a little more care. Now that it's separate, I've made the function even a little bit bigger, right? So first I check if it's specifically float, then we document what we're doing. We like float 32 and float 64. Then we say, hey, if it's not integer, let's do a printf that complains. At some point, we might have an API function for officially registering a complaint or an error from your compile time functions, but right now I'm lazy, so I just printf, right? So here's a printf, and I just try to explain what's going on. Like, look, the modify proc ensure R is big enough only takes int or float types. And then I have an official way of telling the compiler that I do not accept what you're trying to do, which is returning null for any return value. So anytime I return null for a return value, the compiler will register that as a complaint and give you an error message. And we'll see that in a second. Then I do the same thing we did before. Let's look at the type info integer. If it's greater than or equal to 32 bits, we return it. Otherwise, we do different things on signed and unsigned, right? So first, let's look at the regular use. We're using that in the same way, except we're doing something a little more meta here. But for now, let's ignore that. We're just filling these up and summing them. And that's this second 450s, right? The first 450s was our previous test. This one is this one. So now, just again to prove that that works no matter what, let's put ensure R is big enough at the end of the file, and it still works, right? Let's put it into some file called far away, and it still works. So again, I don't remember how to pop the cut buffer in Emacs, so I'm like, yeah. I have a very reduced instruction set attitude toward Emacs. So just like everything in the language works hard to make sure you can do all this stuff with the code organization that you want. So this ensure R is big enough or whatever. This is a toy example that isn't really what you would do in reality, but this could be a part of a library of functions somewhere that you're commonly using as part of a toolkit by name, and it just works. All right, so let's give an example of returning null. So instead of, so here we've said, hey, if info is signed, return S32. Instead of returning unsigned, let's complain. Let's say, you know what? I don't want to accept unsigned types. I'm going to reject this polymorph. And then we return null for t. So there we go. That happens. And it tells us, line 679, a modify proc return null for value 1. What's 679? That's the header of this modify proc, right? And it says it's in response to a polymorph caused here at line 741, which is result B, right? Because result B has the U16. U16 is an unsigned 16-bit number, right? So again, the error message is helpful. It is helpful. Yeah, am I deleting the right thing? Yes. All right. So now let's make the point that we actually did this instead of manually writing loops to iterate and fill the arrays like we did last time. We're actually calling a function fill in sum on the array that also does modify ensure R is big enough, fills the array, and returns sum of A, right? So we're using this function twice. That's useful. And we've got a two-level nested polymorphic function. And so actually, when I got this error message a second ago that was helpful, right, that actually happened 2 levels down. Or no, actually, never mind. That happened 1 level down because it happened in this ensure R is big enough. But, or no, it happened in the other one because it told us. Oh, right. Okay. Yeah. Anyway, so we do all that. Now, so far I've only been showing one modify routine at a time. But you can chain them together, and if you use more than one, they get called in order. So like I said, you can have a toolkit of them that you just apply. So here I've made another one called reject R if float, right? We're only going to look at R this time. We don't care about T. And if it's a float, just return null. And I'm not going to bother explaining why. That's your problem. And if it's not a float, we'll fall through and return R. So now I've got fill in sum 2. And I'm going to first ensure R is big enough, but then I'm going to reject if float. And for array B and C, it'll work fine because those were integer arrays. But A, remember, was an array of float 64. So right now, this is running fine. But if I comment out this one, then my reject R if float will complain, right? At line 759, this modify proc, reject R if float, return null. In response to a polymorph at line 773, right? So that is useful. That's 2 of them chained together. Now, let's do something even more interesting. So far, we've just been doing polymorphic stuff on numbers, but we can do them on anything. Let's do them on class hierarchies, right? And one thing that can happen in a language like C++ is you have some function that wants to do something, like say you've got a game and you've got this entity hierarchy where you could have an entity. Actually, let's talk about specifically what I do here. I have an entity, right? And I have a human, which is using entity, right? So if you missed using, that's in an earlier demo. It's the way I'm using it here is it's like subclassing in C++, but it's more versatile. So I'm basically including entity in this human struct, so human is kind of like a subclass of entity. And then I've got some additional property. And I've got a royal, which is a human, and then it's got this additional stuff. But then I've also got a peasant, which is also a human but has smelliness. And interestingly, I'm putting the smelliness first in the peasant because the smelliness always comes first, which means his offset of his human is going to be different than the royal's offset of his human, which will matter, interestingly, in a bit. So if I'm calling a polymorphic function on these guys, what might happen, especially because these humans are at different offsets, is that you get different code generated for an entity and an entity human and an entity royal and an entity peasant. you might get 4 of the same frickin' function, even if all you're doing is editing the position, right? And even if you deduplicate at the code level, this is going to fail that deduplication, right? Because the human's at a different offset. That'll fool it. So what do? Well, you could, since we are only going to, I'll show you the code that we're actually going to do. We're just going to print position xy like we did before with a label that's some string and then some entity or other thing, right? To complicate it, we're actually going to apply this also, in addition to these entities, to a totally different class hierarchy. That's why we have a polymorphic function, right? We've got a screen rectangle that's got a vector 2 position instead of a vector 3 spatial position for entity. And we've got a textured rectangle, which is like a screen rectangle, but also has a texture map and a scale color ARGB, right? So we can call print position xy on any of these things, which gives us a sort of a duck typing, right? Because we don't care what thing is. All we care is that we can say, you know, thing.position.x and thing.position.y. Anything that satisfies that, we can pass to print position xy. So we only care about position, though, which means if we're given an entity royal, we really only want the entity, because that's where the position lives. And if we're given a textured rect, we really only want the screen rect. That's where the position lives. So in order to reduce code bloat, right, and reduce compile times of generating the same function all these times, what we want to do is navigate to the base class anytime you pass a derived class for this thing, right? So first, in this first example, you can see there's no modify proc, and we don't do that at all, right? So let's just show we're calling print position xy. Make sure it's working again, right? So we're calling print position xy on a royal and a peasant and a rect, right? Remember, the rect is in a totally different hierarchy. So what we get is royal is of type entity royal, right? We're getting that by we're assuming it's a struct, which is a little dangerous. Again, you would type check this if you were being careful. But we're assuming it's a struct, and we're saying, you know, that info gives us the name. We're also passing this string label that the user gave us, which is down here. And then we're printing out the position x and position y, right? So a royal is an entity royal, and a position is x and y, and a peasant is an entity peasant, and there's the position. Those are both 3D positions, and remember, these are our default values for vector 3. But the rect is a textured rect, and it's got a vector 2. So the code's working, but we don't necessarily like it, because we're calling different versions of this function for 3 different types, which means we're generating 3 different versions of the function, and that's no good, right? So just to show that, down here I'm baking it. I'm baking one for entity royal and baking one for entity present or peasant and printing out the pointers to those 2 functions, and they are different. They are different. However, I defined this function, go to basemost struct containing member, right? Which, let's just look at this whole thing as a little bit of a review, because I basically covered everything that you need in order to do this in the demo called, you know, runtime and compile time type information. But it's pretty quick, so let's look at it. So first, I'm calling this function getField. We're saying get a field, the field that we're looking for by name from this struct. And if it exists, just return that struct, right? So let's look at that part. Well, no, let's look at this, okay? So we do that. If it exists and it's not imported from another struct, right, which is like if it's not a derived member, then return that. Otherwise, we're going to recurse into all the members of this struct and search for this thing by name in all those members, or if those members are not structs, if they're like floats or ints or something, just skip them. Then we know the member's a struct, and then we recurse into here in that member. So we're recursively navigating down the class hierarchy. We could do the equivalent of multiple inheritance with this, etc., right? So let's look at getField for a second. It's pretty simple. We just say for everything in the members array of this info, if the strings match between the name, actually I wrote this before I made string compare work with double equals. This could just say if it.name if it.name is equal to name. But I actually wrote a strings match at user level before I had that, and there that is. So anyway, this is doing a classic style string compare. Anyway, so if the names match, return it, otherwise return null, right? And here's has field is built on get field, right? So we're just get field assumes we're a struct, and has field says, well, maybe we're not a struct, and if we're not a struct, return false. Cast us to struct, and then do that stuff. And then is imported just checks this flag. And actually, I used this hack because I didn't have bitwise and when I wrote this, but I actually have bitwise and now, so we could have done that properly, but I didn't. Anyway, so let's go back to this. So this function is now, to nobody's surprise at this point, hopefully if you're following, going to be employed in our new version of print position xy. So now I've got to modify proc, and I'm just writing it inline again because I don't want to have too many names cross-referencing other things. So I've got some type t of whatever thing is, and it's a type info. And if it's not a struct, I'm going to give you an error myself, like, hey, you must pass a struct, and I'll return null so that the compiler exits and complains. But assuming you gave me a struct, I'm going to go to the basemost struct containing the member, where I cast it to a struct because I know that's what it is, and I want the member position, right? Now, if you gave me something that doesn't have a position, I'm going to return null. Otherwise, I'm going to return the info member of the base class. Info is just I didn't do this to do. Like, I'm not sure why this autocasting. I should be able to return a derived class of info, but I couldn't. I had to dereference it explicitly. So that's a minor compiler nit. But anyway, so I'm returning that. So the upshot of this, after this very long explanation, it's actually pretty simple if you just think about what it does straightforwardly. Now I can print position xy on a royal, and it's actually downcast to entity by the modify function, right? But it still works. I get a 3.0 and 3.1. Peasant is downcasted to entity, so I get 3.0 to 3.1, which means, and we'll verify this, going back to those diagnostics we had before, this means we're actually using the same code for both of these, whereas we wouldn't have been able to use the same code before, right? But we can also use that on any hierarchy, right? If that's all we wanted was to take an entity, we didn't have to be polymorphic at all. We could have just made a function that takes an entity, right? But we want this to work on anything. So here's a screen rect, and or a rect, which remember was a textured rect. That's what type it was. But textured rect is a subclass of screen rect, or superclass. Which one is which? I don't know. I don't like object-oriented terminology. Anyway, derived class of screen rect. And so we've gone to the base class here, right? And that works. So let me turn on those diagnostics again. Let me make sure this still works. Demo, poly pre-build, and I'm going to turn back on the polymorph match. And let's look for what we want to see is line 895 is matched to line 894. Right? So please work, please work. There we go. 895, polymorphic call matches 894. What you won't see is these matching, except there's another point to make, right? Excuse me. So these won't match, right? So this is line 856, and that will not match 855, but you'll see it, 856 actually does match 860, right? And line 860 is this bake. So this bake, like baking a function and calling it do the same thing, and the bake gave us the same thing as the natural polymorph did, or whatever you would call it when you just call a function, right? But ideally, all four of these, this, and this would have done the same thing, but actually we got two different things. So the compiler does what it can, but you can help it out, in this case, by doing a modify. So I think that's pretty cool. That's something that I, I think is a very expressive thing, and to just be able to do that with everyday code is cool. All right, so now let's move on one step further than that, or one step more general. That was a very specific use case. But like I said earlier, C++ has this whole thing called concepts that's very complicated. It's so complicated that it didn't make it into the last proposed version of the language. They had to cut it from the spec. Maybe it'll make it into C++ 17. I don't know if C++ 17 even happens in 2017. But the idea behind concepts is you can specify an interface, and you can say, hey, does this parameter match this interface of this template function, right? Well, given what I've shown so far, we can do all of that at user level. And I haven't built everything that C++ does, but I've built like a subset of it that I'll show now. So here I've got an entity that's got floats of x, y, and z. And again, I've got some derived classes like human and royal. So that's in the same chain as before. And then I've got one called lame that's got an x, y, and z, but they are ints. Now, remember, I've got a vector 2 that's got floats of x and y. And I have this function called, oh, I guess it's elsewhere in the file, where I've got a function called satisfies interface that we'll look at really fast, but it's similar to what we just looked at, right? Satisfies. So satisfies interface takes two general type infos and basically makes sure they're both structs, returns false if they're not. Otherwise, it calls this other thing by casting them, right? And satisfies struct interface just says, okay, we've got some variable that came in, and we've got a target struct that we want to know that it satisfies. And for every member in the target struct, see if the source struct has that field. If not, return false. Or if it has a field by the same name, but the types are different, return false. Otherwise, return true. Now, this doesn't care anything about the offsets into the struct. It just cares about their position in the struct. If we cared about the memory offsets, we could do that as well. But this is sort of a very light duck typing of like, do these things have the same names of the same types, right? So, whoops, I'm calling this one. I was trying to get back to where I was. All right, so we've got these tests. Does vector 4 satisfy vector 2? Does entity royal satisfy vector 2? And does lame satisfy vector 2? And these first two should, right? We're calling satisfies interface directly. You know vector 4 has an x and y. Entity royal is a human, which is an entity which has an x and y that are both float. And lame, however, has an x and y, but they're int, right? So that should not satisfy. And you'll see in the output, where are we? Oh, did I quit? Hold on. I quit before it was done because I had it running through more. There we go. So does vector 4 satisfy vector 2? Yes. Does royal satisfy vector 2? Yes. Does lame satisfy vector 2? No. So that's cool. And now we can use that in a modify function. And to make it spicy, I'm going to make a deep chain of polymorphic functions for deep and call it in a way that makes an error. So now I'm going to have something like a vector 4 I'm going to call top. Top is going to take a thing. It's just going to print in top and call above middle. Above middle is just going to call below middle. Below middle is going to do something useless and call bottom. And bottom is going to print the x and y of this thing. And we've sort of changed the name of the type a couple times along the way. You know, we're being needlessly obtuse, but the whole point is to just make something for deep. Now that works on a vector 4, right? So notice I say top of v4 and I say in top, x is 4.0, y is 4.1, right? 4-dimensional vector x and y. So that's good. Wow, C++ people must be really confused because they always think vector is an array. Vector here is a math vector, like all good game programmers know. Anyway, so now let's call this in a way that generates an error. So broken here is just a regular struct. It doesn't have an x or a y. And so we're going to get an error message. And it so happens that because compilers are complicated, I'm not going to give a very good error message right now, because I haven't gotten to this yet. Basically, line 955, undeclared identifier instruct x and y. And it's like, okay, But who generated that? Where did this come from? And the reason that's a bad error message right now is that dereferences of structs come at a later time in the pipeline where I haven't kept track of this information. And later, we'll make a good error message here, and we won't need to do what we're about to do. But we can do the equivalent of C++ concepts to catch the error at the top instead of at the bottom, right? So I'm going to make this function satisfies vector 2, right? Remember, we had a general satisfies interface. So satisfies vector 2 just says, okay, if this type satisfies the interface of vector 2, return that type and we're fine. Otherwise, return null and complain, right? So now I'm going to take this modify and put it on top, right? So now we've got a modify of satisfies vector 2, and then all these others are just regular vanilla polymorphic functions. And there we go. So we're calling it, and it says, hey, struct does not conform to interface of vector 2. Modify in line 554, return null for value 1, right? Line 554, whoops. Sorry, 954. I was being dyslexic. 954 is there. And the polymorph was caused at line 994, which is there, right? So we found our bug, and we recommented, and it works again. So that's good. So there you go, C++ concepts. You don't have to wait till 2017 or whenever. You know, to be fair, C++ concepts are more complicated than that, but I'm pretty sure anything that they can do, you can do with what I've just showed. Okay, I'm going to take another bite of cupcake and then keep going. It's a good point. Some people have pointed out that for what I said to be true, this language has to be released before 2017, but that is the plan. Okay, so that was modify. By the way, we're probably over halfway done, but it's been a long time. So this is, I'm just putting this forth to you right now. This is going to be a long stream. That's just how it is. Let me check OBS and make sure it's recording. Yep. And this is going to be a long stream, and I'm just getting it all out. Now you know why I'm doing function polymorphism and types like struct polymorphism in two different pieces, because there's going to be a lot to say about structs too. All right. Let's do some robustness tests. This one should go quick. Let's see what that prints. So we've got a couple factorials and stuff. So here's a polymorphic function that's recursive. Excuse me, recursive. And if our compiler is any good, it should be able to do that, and indeed it does, right? So classic factorial, but we're doing it in any type. And we're carefully, you know, we're not specifying these literals if they're int or float. So this will run on int or float. So here's an int factorial, and here's a float factorial, and we're doing 8 each time. So hopefully that's the right answer for 8 factorial. I guess it is. So that's cool. Now let's do something that could totally make a mess if the compiler wasn't kind of robust. Here we've got a function called make a mess, and it's got a modify proc that tries to call make a mess. So it's a recursive, it's an infinitely looping recursion at compile time that could never terminate, right? And it's not even all in regular code, because a modify proc is kind of a special thing. So what happens? Well, what happens is you get a circular dependency error, which is a different kind of thing that I haven't shown yet, I don't think, unless you've watched the just general compiler development streams. But basically from this you can suss out what happens. You know, hey, the function make a mess depends on its modify, and the function body of that modify depends on make a mess. So right there, that's circular. And you get the locations for all these in case the description isn't good enough. So that's circular, and that just can't stand. So that's fine. It doesn't blow up, the compiler doesn't crash, etc. It gives you something that you can use diagnostically. All right, so here's one. It's the same thing, but I've put an intermediary function to try and trick it, and it won't trick it, right? So now, instead of the modify being inline, I've done it by name, and it's a modifier, and it's calling an intermediary that calls make a mess. So we've just inserted more stages, and again, we get a circular dependency error. So that's fine. Modifier has got to be a procedure, so if we do make a mess and we modify with the number 51, it's going to complain about that. Expression in modify directive must be a procedure. So just because this is metaprogramming or things that happen at compile time doesn't mean that your error messages get more crappy, as they seem to in some languages. Good error messages, except for that one that I'm going to do later. All right. So here's one, the whole point of which is to be annoying and obtuse, right? So I've got this inner func, which just prints an int and a float. I've got this thing called double steal that takes a function argument, that's some function that takes a float, and another function that takes an int and some type. This is going to be the inner func that matches this, right? And returns void. And the outer func returns 2 of whatever that argument to the inner func was, which is going to be this, right? And by the way, there's another argument whose type also matches all that. So this is starting to be a kind of an involved type match, right? We're going down 2 levels of function parameter nesting to get that this type is authoritative. We're matching it to return types and then like another argument in the top level function. And so we just verify that that works, right? Double steal of argfunc and 4 is going to call inner func with 1 and a float 4.0, right? We're ignoring the return value. That's just there to make this more complicated. And that should print 1 and 4. And indeed, well, if I turned off the other thing, there we go, 1 and 4. So if you start messing up or whatever, it's pretty robust, and it's robust to relatively complicated things. Of course, somebody at some point is going to start throwing things at it that break it, and we'll deal with it when that comes. But the point is just, this isn't a simplistic, hard-coded kind of type matching. It's full, recursive, arbitrary depth pattern matching. All right. Baker test. This is another sort of robustness test, but I put it on its own. Here's a function called Baker. It takes one argument of any type, and it returns a function that takes account some integer and an argument of that same type and returns void. And what it's going to do is it's going to bake this procedure that's meant to operate on that argument type, right? And all it's going to do is it's going to do a printf count times. And again, because I'm just going to be sloppy and call this once with float and once with int, I'm going to printf the number twice, and just one of those times it'll work out, right? So Baker is baking a function and returning it, right? And then we're calling it. And again, this is happening at compile time, right? This is not a closure or some other kind of higher level thing where we get slower because we're doing this. It actually, it's the same as if you had hand-typed these functions as far as the compiler is concerned. So let's verify that that worked. Here we go. The first time we call proc a, which is a baker meant to operate on I, or any int, right? We're going to call that on I, which is going to print 42 3 times, and that's what we get. And then on a float, we're going to print 24 as a float 4 times. So there you go. And I can operate on some other int, so I can go 278. That's an integer, right? And there we go. So, you know, this is some kind of like function factory that generates other procedures, etc. So that's cool. Let's test interactions with other things in the language. As we've shown, it already works with using. There's sort of two flavors of using, where you say using in the parameter list or where you say it in the body. It's actually non-trivial to make that work, but it works. So here I'm calling using tests on these vectors. Why did I interaction? Put it outside the comment. This is why syntax highlighting is good, because I would have caught that. Okay, here we go. So these using tests are just printing the x and y's. And as we showed last time, we have named and default parameters, right? So let's do a polymorphic function and use named parameters and default values. So here I'm going to make a function that adds the z components of things plus maybe an extra value that's default is 0, but I could pass in a different thing for extra. They're all of different types. We have 3 types, T1, T2, and T3. But T3 determines the return type. Now, we're going to give it a modify proc, right? And what the modify proc does, I'm not going to go through it because it's just the same thing we've already done. But what we do is we say, whatever struct you passed us, well, if it's empty, we're going to complain. Otherwise, we're going to look at the type of the first member, and we're going to return that as both T1 and T3, right? And then T2, well, that's whatever you passed because we didn't specify it, right? So what that means, and I'm not going to exhaustively, because we're doing a lot of examples, but you could have vectors of doubles, right? You could have vectors of ints. You could pass them, vectors of float 32s. You could pass them all to add z components and they would all work, because this is picking whatever the value of the first member of the vector is. You could also look this up by name or whatever. So here we're adding the z components of v3 and v4, right? And so you can see that works. We're adding the components of v3 and v4, but plus this extra that's 5. So that's 5 more than the previous number. That works. And now we're going to specify the arguments in a totally different order. So extra is 1, and then v2, and then v1. Right, with named arguments, you can put things in any order. And this is correct. You know, we're multiplying by different factors, so the number comes out a little bit different, but those of you watching at home and screenshotting can verify that that is correct. Last thing to show here, well, here's a function. We're going to print the xyz of a vector again. The vector is, well, it's some pointer to a vector, and I'm going to call it with v3, which is just a regular vector 3 like before. All right, so there's v3, but I'm also going to call it with a vector in SOA format. Right? Remember, SOA format stores all the x's and all the y's and all the z's. Here's an array of SOA vector 3's. If you were to naively take just a raw memory pointer into the middle of that, you'd see like a bunch of y's or z's or something. It would be wrong. However, here it's not wrong because we generate 2 versions of this function, right? One for the non-SOA and one for the SOA, right? So this polymorphism can help your code deal with any complexity that might pop up of wanting to be SOA, in addition to all the cool stuff that we demoed back in the SOA demo. So yeah, people are asking about parameter names in modify proc, so I'll specify that. Right now, the modify procs are a little weird and different from what you're used to in that the names are what the compiler cares about, right? So if you name something T, right, or my type or whatever, then you need your modify proc to have that parameter my type. And the reason I did that was because it seemed, if you just want to say, you know, if you just wanted a situation where you just say modify and then some name, right? I didn't want you to have to specify all the arguments in a certain order or whatever, because there could be a lot of arguments. You know, you might want to ignore, I don't know. I mean, if we don't like the name thing, which I'm not sure if I totally like it or not, because it might make it harder to reuse functions. Like you might have to make a wrapper with parameters of different names. But you could imagine having a slightly more verbose syntax where you just do this, right? And then we don't care what the names are anymore, and then it's parameter order. But for now, yes, it's actually matching the names. And that's, so when I had multiple types like T and R and whatever, it was matching the names between those. All right. So cool feature, body text. Did I do the same thing? Okay. Body text. So, rather than having a modify proc that just modifies things and then passes it to a regular function body that's below that, you can have this body text directive that replaces the function body, right? And like a modify proc, it takes the types and it returns a string, and the string that it returns is then fed by the compiler back into the compilation loop, right? So here, let's show an example of that. This is not the right way to write this function in reality. It's a little bit goofy, but it's an example, right? So, okay, so we're printing lengths of vectors. And again, if you're following along at home, those are the correct lengths of the vector 2, 3, and 4 that we defined, I hope. And what I'm going to do is I'm going to build a string for each of these types, right? So if I call length with a vector 2, I'm going to generate a string representing the function that gets the length of a vector 2, right? Etc. Now, the reason I'm doing that here, I mentioned at the beginning of the talk that you already could sort of do this by just generating a bunch of stuff from a build proc or whatever, like when you start compiling the game. But because this is a polymorphic function, it not only gets generated at the calling site, right, but the error message gets traced directly between this piece of source code and the calling site, right, which is helpful. You might, again, there's this great separation in time and space between stuff done with the other kind of metaprogramming. So this is a bridge between those two, right? It's a bridge between arbitrary code generation and classical, template kind of thing. So here's what we do. We start out with a string that says x times x, and I'm just going to leak these strings. In reality, you'd have a string builder, that's careful, and then you return this thing, and the convention would be that you return something allocated with malloc, and then after the compiler compiles it, it would free it. So for every field we have, if we have a y coordinate, we're going to add y times y, like plus y times y. If we have a z coordinate, we're going to say plus z times z. If we have a w coordinate, we're going to say plus w times w. Then we're going to insert that string into this other string that says return square root of that stuff, right? So now if you want to visualize what text we're actually generating, right, before we were just printing the results. But because this is an arbitrary imperative code, if I'm confused about what's being generated in response to my polymorphic call, I can just print it out, right? Printf debugging. So here I go. So for the first time, I generated square root of x, x, y, y, right, x, y, z, and x, y, z, w for a 2, 3, and 4-dimensional vector. So that's kind of amazing, and it works. So let's see what happens. Let's call it on something that's not a vector first. So malloc is not a vector, that's a function. So if I take length of that, what happens? It'll complain. Well, let me get rid of this so I'm not spamming the output. Let me get that further down the screen in case my picture is covering it up. Okay, so it says length wants a vector type, but you gave it something that wasn't even a struct at all. The body text proc returned null, so that's rejecting the types just the way that modify can reject types. And that was in response to a polymorph at line 1448, right? So as we said, that won't work. So now what if we make a typo or something, like what if we say return squaredf, which is a function that doesn't exist? We get in this location thing on the left where it usually says the file name, now we say from a string, it's line 1 of the string, character 15, undeclared identifier squaredf. But even though you might think that you'd be lost because there's just some random string that we're compiling, we know who generated it, right? So this is why this is helpful for day-to-day programming, right? Oh, this was generated by this body text directive at line 1414, and here's the site that called the polymorph at line 1442, right? When that string gets inserted into the build queue, this location information rides along as a tag, so we can reference it later. And that's true, like, I can do some other arbitrary, that's not going to work either, and, there we go. We still get that information. Okay. Now, this is building a string and running the string is kind of overkill. That's kind of big guns to bring to any fight. And a lot of the time you don't need it, right? Most of the time you probably use the facilities that I covered earlier, but it's a very powerful technique, right? I didn't implement for this talk some techniques that are sort of subsets of this. Like with body text, you're generating something completely unparsed. You could imagine something that just inserts part, that's like a static if, that inserts expressions inside something, right? So you could imagine something where you have like a body and you do some things, right? And then you say, you could say block if, some condition like is not float t, and then some block do A, do B, right? So I didn't implement that for now, but this is actually an easier subset of body text. It's much easier because this is already parsed. So this could just go in, So this will probably happen, but I wanted to demonstrate the most powerful, most general one today, which is this one. All right. So that is body text. Now, bake values. This is another one of my favorite features. So far we've been talking about polymorphic functions, right? But polymorphic functions are mostly like regular functions. They just take type variables, right? Well, once you've done that, once you have it so that there's not much of a difference between polymorphic functions and regular functions, you can start treating regular functions like polymorphic functions and do cool stuff with it. So here's just a function called multiplier. It takes an a and a b. They're both float, and it returns a float. And we return a times b. Very simple function. Not polymorphic at all. This won't work on integers, right? There's no type variables here. This function could have been written in any of the previous demos of this compiler that I've shown you, right? So now we're going to take two floats, 3 and 5, and call multiplier on them. And as you see, 3 times 5, 15. That is as expected. Now, I'm going to use this directive called bake values to make something called muller, which is multiplier, just a regular function, but baked so that b equals -9. What this returns to me is a function with b pre-applied, right, where I only pass one argument, right? So now if I pass muller of a, right, we get a times -9, which is -27. If I pass b, we get 5 times -9, which is -45. This is not a closure, right? In lots of like higher level soft garbage collecty mushy gushy languages, you can do this thing where you wrap a function inside a closure and you return the closure and then that value is in the environment, but that has compile time cost, right? Here, we're pretending multiplier is a polymorphic function. We're generating a new version of multiplier at compile time that is more specific to the case that we want, right? And then I can do that again. I can make something mer that's baking muller with a equals -11. So now we get a 0 argument function that we can just call, but it's going to be -11 times -9, which is 99. Now that is pretty interesting to me. I like that a lot. You can do this with any function in your code base anywhere, right? Completely unlike C++, where if you didn't declare something as a template and take all the resulting ugliness, you're out of luck, right? Now, why would you actually want to do that? Well, we'll say in a little bit. Now, you could have done this before, actually, because remember we have force inlining, right? And so you could have made a function called Muller that's equivalent to what we did up here, that takes the same argument list as multiplier, and then you just say inline return multiplier of a and minus sign, and because this is inline at the calling site, then we're guaranteed to bring this in. But point one is this gets a lot more cumbersome as this function gets more complicated. Like, why should you have to type all that stuff? You just want to specify one argument. But also, you know, if you watch a C++ lecture by Chandler Carruth or something like that, he'll all be talking about optimizing your C++ code and how it's important for the inliner to be able to activate things, because if the inliner runs, then you can fold all these things and get faster code. Well, a thought that I have in response to that is, hey, wait a minute. Why is this optimization dependent on the inliner, right? If I want something to be fast, I want to know that it's fast. I don't want to, like, maybe the inline will happen and maybe this will be fast, right? So the case where I want to specialize a function for specific values in a clean language should be orthogonal to whether that function is inlined or not. Maybe I want that function to be fast when I get there, but I don't want to pull its body into my own function and make my function gigantic, right? That can be counterproductive in many cases. So, this is not, I think, the cool usage case of bake values. This is an example to show you the concept. The cool part is this. It's when I can start writing functions that are general, but have complete faith that I'll be able to use them in specific cases and not pay for the abstraction penalty at all, and not have to write wrapper functions that do weird things. So I'll give you an example of that. I've got this function print names and values, and what it does is you'll see all these different variants of like this. It's printing all of these. And what it does is you pass it an array of names, an array of values, and some spacing mode, which is one of these enums of none, indent, or exdent. And you know, if the mode's exdent, then we print this out further, and then the array of things, cow, pig, horse, in. And if it's indent, we do the opposite. And if this Boolean use dots is true, then you know, we print dots here, otherwise we print spaces. And that's how we're getting all these variants. Now, you may have noticed this funny $$ up here before the variable mode. And what that means is anytime, anywhere in the program where you call print names and values, if the value that you're passing for spacing mode.strict is known at compile time, actually right now we don't do a lot of analysis, so it's just like if you pass it as a literal, right, like one of these, then auto bake this function so that only these are really the parameters, and this one is hard coded so that the code gets generated with mode as a constant, so that you don't have to pay for these if statements, right? Now, so then, you know, it's like saying if you pass indent, then this would basically be an if 0 and this would be an if 1, which allows you to get rid of the branches in most cases. Now, in a stupid function like this where you're printing things, you don't care, but there are a lot of cases where you start writing a complicated function and it's got a few different use cases, but you would like it to be fast, or you would like it to be small in terms of polluting the code cache for one particular use case. And this gives you a way to manage that that's orthogonal to inlining, right? This doesn't have to be inlined to get the benefit of a fast version for a particular constant. And it's controlled by the programmer, so you know what's happening. And in fact, we have those diagnostics info printouts. So let's just, you know, first of all, look at the usage. So we've got an array of names, an array of values, and we've got some animals, we've got some numbers, and we're just printing those first with no indents mode, and then indent mode, and then exdent mode, right? And the first two, well, we'll talk about use dots in a second, but for these first 5, we're calling it with indent modes that are all specified on the argument list, So they're all very obvious. The compiler knows exactly what those are. And then the last time, we don't know what it is because it's in a variable. I mean, it's right here, but like I said, we're not doing analysis at this level of the compiler right now. So for all the compiler knows, this is unknown, right? So now, as you can see, though, the code works. It does these, right? Now let's turn on the diagnostic for what's actually happening. So we're going to go back here, and we're going to say our build options tells us about auto value bakes. What happens when we do auto value bakes? Well, let me clear. All right. So it's telling us every time there's a value bake. These two are actually manual value bakes from the previous function. But once we get to line 5061, that's what we're talking about. It says, hey, this variable mode is triggering an auto bake. And we did it successfully. Now there's one variant of this function, right? So let's go to 1561 in that file. So now there's one variant. So now this bakes another one. Now there's two variants. Indent is the second variant. Xdent is the third variant. But now we get to the next one. We're triggering another auto bake, but it's a duplicate, right? Because we already had one for indent. That was up here, right? All these other parameters don't matter. Those are just still parameters, right? And then this one is still indent also. This could be xdent. It doesn't matter because we've already baked those. So just like with a polymorphic function, we only generate the code that we need to cover the cases that we want. Okay, so now I have this very versatile thing. Like suppose I come along one day and I say, you know what? These if statements aren't the ones that matter on this particular architecture, or maybe my usage has changed. Now I care about this one really bad. I care about use dots. So I'm not going to auto bake that. I'm going to auto bake use dots, right? Immediately, very simple change. And yet I've got a different set of functions that are now generated, right? So here, let me run it again. And now use dots is triggering auto bake instead of mode, right? And we bake two variants. And in the cases, by the way, where we can't, like down here, I've switched to a variable. The first two I'm calling with false and true. So again, the compiler knows what they are. Once I start calling it with a variable, it doesn't know. And of course, in that case, it calls the non-baked version that just has all, right? So really, there's three variants. There's two that are baked and one that's unbaked, right? But we get told when it can use which one. So there's no mystery, right? We don't have to like rely on a mysterious optimizer doing mysterious things and look at the assembly code. I know what's happening and I can do it by hand. And if I want to go bananas, I can actually put this on both of these, right? And get combinatorics for, I can bake based on both of those. And now I'll run. And now I'm auto baking on mode and use dots. And I get four variants, because that's what's required to cover the cases that I used. So that is, in my opinion, pretty damn sweet. I enjoy that feature, and I think I will use it. Because what it means is, you know, all the time we write, you know, we'll put if-defs around something to try and, you know, if-def things out to make it faster or whatever, right? You don't need that. You just... you know, when you've specified a constant here, it's exactly the same from a code generation standpoint as if this wasn't a parameter at all, and it was like const mode is whatever down here, right? So that is autobake. We're getting toward the end. Okay, map test. So that's officially all the features. Autobake is the last feature. But now I want to look at another use case that's maybe enabled by polymorphism and see how it goes in a language like this. Let's look at what the output is here. Clear. All right, so we're printing a bunch of things. Again, let's look at what those are. They come from an experiment to do programming in a style a little more like Lisp, right? Like the philosophy behind Lisp, or one of the philosophies, is that it's a powerful thing to just have an array full of stuff and map that array to another array. So you like iterate over the thing and you turn it into another thing. Actually, with Lisp, it was linked lists usually and not arrays. And the problem with that is that they're very memory poor. So in the modern day, a smart version of that would be arrays most of the time. So we're doing it with arrays here. And what does that mean, right? So first of all, we're a strongly typed language. So we're going to use polymorphic functions to map over arrays, which means we get type checking, which you didn't in Lisp or most Lisp-like languages. And we'll look at the other ramifications too. So here I'm just going to make an array 5 elements long of integers. I'm filling the array with its index plus 1, and then I'm printing that array out, right? So that's this A sub whatever is whatever, right? So A 0, 1, 2, 3, 4 is 1, 2, 3, 4, 5. Now, I've got this function map, which is polymorphic, right? It takes an array of some type and a function that takes that type as an argument, or an element of that type as an argument, right? And returns an element of some other type. Now, map is going to allocate a new array, here with malloc, but we'll change that eventually. We're allocating a new array of the same size, but big enough to hold r's instead of t's. And then for every item in the source array, we're going to say the result at that index is what you get when you apply f to that element, right? So we're returning an element of, or an array of r's where each r corresponds to the t in the array of t's. That might be a little too abstract, but to start out, we're simple. So remember, we've got an array of ints here, right? We've got 5 ints, and we're going to take a function that maps int to int, square here, right? So square takes one integer, returns n times n. So now b is map square over a, right? And then we print out b. So b is 1, 4, 9, 16, 25, right? So we're taking a function that operates on an individual element and applying it to a whole group of elements, which in some sense is a very powerful high-level thing to do, in some sense. In this particular case, I could have just said for a blah, 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 right? But as your functions get more complex, it becomes more worth doing this. All right, so now I've got a function Stringify that makes this string saying the number and whatever and returns that, right? So C is going to be that. So I've got the number 1, the number 4, the number 9, etc. These are all strings. Then I've got this thing called reverse, and I have to apologize because I'm not totally consistent with string handling. So some of my functions like mprintf, yeah, I mean, you can't really index a string as an array right now because I haven't decided what the final storage format of a string is. So cast to pointer to U8 and cast back. But to reverse a string, I'm allocating something of the same size, and I'm dropping the characters in the reverse order and zero terminating it. We may not have zero terminated strings eventually, but that's what they are now. They're exactly C strings. So I call reverse. D is mapping reverse over C. And there we go. Right. Now, if we stop right here, we just leaked all that memory, right? Like in Lisp, you would do all this stuff, and then sometime way later, a garbage collector would run and collect all your garbage. And that's fine if you don't care how fast your program runs or how responsive it is. But I care about those things. So here, I would have to manually clean up that memory, which isn't totally great. I'm going to skip this because it's been a long talk so far. Okay. Now the thing is, even doing this cleaning up after ourselves is not great because malloc, if you can avoid calling malloc all the time, you should, because malloc is slow, right? So all other things being equal, we would prefer not to call malloc. So we'd prefer to make a different allocator that's fast and that we can just wipe the things away. So to do that, we have to have a slightly more cumbersome version of map, where now we're passing the array, but we're passing a function that takes that type and also an allocator, and then map is going to allocate the result array with that allocator also, right? So instead of calling malloc, we call this alloc right here. And then we pass the alloc to the function in case the function needs to allocate also. So let's look at what allocator means. That's just, I'm not going to go into this. This is just a syntactic thing for right now. That's probably not permanent. But an allocator is just a function that takes a size that's signed 64-bit and returns a void pointer, right? So now we're passing these allocators around, which is slightly non-ideal because we've got an extra parameter, but they allow us to do some interesting things. Our square has to take an allocator, though, because like that's our signature that we're trying to match for this function takes 2 arguments, and so we kind of need one there. Here's our new Stringify and our new reverse that all take allocators, right? Pretend that I had an mprintf that takes an allocator, but I didn't, and I didn't want to make one. Eventually, when I decide, like, I'm not going to be using printf forever. I'm using it because I have that from C. But eventually, we'll have a safer printf that's nicer, and it's safe to say it'll take an allocator as an argument. Anyway, so here's our new reverse and our new Stringify that take allocators. Now, interestingly, if I knew that these were all going to get inlined, like if I could inline the map and if I could inline this argument, then I could use alloc A here, and I don't have to deallocate anything, right? Alloc A allocates stuff by putting things on by moving the stack pointer, basically, by the amount that you need to store your stuff. And then when your stack pointer gets popped, you're all good, right? So that's very interesting that we could do some very high-level Lispy things at basically no memory allocation and deallocation tracking cost, right? This is better than RAII things, because RAII stuff is probably allocating somewhere inefficient, and then it takes time to clear it up or whatever. Now the trick is, though, because this function is an argument to map, then we have to know that map is inlining this and that this inlines everything down to the allocator. So you'd have to have either a map inline function, or maybe you'd have a syntax where you can tag a function pointer as inlined, maybe, right? I don't exactly know how that works and in what cases it could work, but you might be able to do that where you say, I'm going to inline map, but I'm going to pass it inline reverse, which means when reverse gets applied, force that inline. Again, you probably need a diagnostic printout so that as the programmer, you're sure that that gets inlined. But if it does, then you can correctly use alloc A, and your program is correct and maximally fast, which is cool. That when I thought of this, I was like, oh, there's an unexpected use of call site inline that I didn't think of. That's pretty sweet. All right. However, you know, we can also, if we don't want to pass allocators all the time, you can also have them be default arguments, obviously, like anything. So here's a reverse array function that reverses every element in the whole array, right? We already reversed the string within the array, but now we're going to reverse the order of elements in the array. And it takes an allocator, which is some function mymalloc if you don't specify it. And we call that, right, instead of malloc. And we've got another function that converts a string to all caps, right? Again, using an allocator. I didn't specify a default this time. Now, instead of using alloc A down here, like here I did B, C, and D again. Like last time I pasted all this stuff, we did B, C, and D and then freed them. Here I've got a new B, C, and D, but because we've already seen all that, I didn't print it this time. So I compute it, but you know that it's correct because after D is done, I'm going to do an E and F based on D, right? So here for E, I'm not calling map, I'm calling reverse array on D. So now the elements come out in the opposite order, like we go here. So the 52 is first and the 1 is last. And then for F, I'm mapping over E and turning all the strings to all caps. Now, here I'm specifying an allocator of my own called pool alloc that I'll show you what it is, but it's a memory pool that starts out empty. I allocate into it very fast, very contiguously, and at the end of this I call reset, right? So there we go. I've done this very Lispy, very mappy kind of thing. It's a little more cumbersome than in Lisp, but it's a zillion times faster than in Lisp. And in future versions of the language, depending on what our priorities are, we might have some kind of way of implicitly setting allocators or passing them around in a hidden way like this pointers usually would be, that then relieves this burden of having to do this all the time because allocators are important. So as a last thing, let's look at the pool, right? The pool is a global variable. We'll look at that file in a second. Pool alloc is just an allocator, right? And it calls get with the pool and the size. That's all it does. And in pool, This is some struct that keeps arrays of memory blocks of 64K unless you specify a bigger size. And when you call get, right, these other things are about resetting the pool and making new blocks. But when you call get on the pool, if we have a current mem block that's big enough, we use it. Otherwise we make a new one by calling cycle new block, right? So that's ideally, if you have enough room in the current block, that's a very fast allocator. And if you have to cycle a new block, you end up, here I'm calling malloc, right? Or you probably could set the allocator on the pool if I had provided that. But you only call malloc once every great many allocations, right? And that's what makes it fast. Okay, that's everything I wanted to show today. We got through it. It's only been 2 hours and 15 minutes or something. Thank you to everyone who stuck through the whole thing. This is going to be on YouTube for anyone who missed parts of it. And I'm going to take another voice break for a few minutes. And then I will be back to take questions for anybody who soldiered all the way through all of this. And we'll be very thorough about question answering this time because we've got all the time in the world now.